It seems to be working. Did you say something, Ryan?
Can you hear me?
Sorry.
Can you hear me? Yes. Great. Thanks. All righty. Let's get started. All right. So welcome to lecture 2. Today we're going to talk about largely supervised learning. But since we only covered half the slides from last time, we're going to kind of get through the rest of our formalism, and then we'll start studying supervised learning. All right. So structure of our lectures, we're going to start with a little bit more about MDPs. I'll recap what we covered last time. And why we should care about any of this, right? Few motivating applications and scenarios, and then we'll get into the formalism of imitation learning. I'll tell you about some fundamental challenges in imitation learning and how we might be able to fix them a little bit. Yeah. Okay. So let's kind of recap what we did last time. Last time we talked about what reinforcement learning is, kind of our informal definition. We have an agent interacting with the environment. You observe the states of the world. You take an action. An agent transitions to a new state, providing you a reward in the process, right? And then the goal is for you to try and learn a strategy that gets you as much reward as possible. And so really the goal is to try and learn without an expert corpus, to learn in arbitrary settings while generalizing to new states and maximizing some notion of success, right? So that was the intuitive definition. And the hope was that we could use this for continual learning or for learning behaviors and environments that are hard to analytically describe, right? Okay, and so the formalism we decided to use was this thing called Markov decision processes, or MDPs. Does anyone kind of remember how this works? Yes, no, thumbs up, thumbs down. Okay, so in MDPs, you're going to have states S, you're going to have actions A, reward R, and you're going to have transition dynamics, which are going to tell you if I was at state S, took action A, how would I transition to state S prime, right? And so those can be stochastic or deterministic, both work, but we're going to try and use this formalism. It's like a Markov chain with two additions. The first is action, which allows you to make decisions in the world, and the second is reward, which tells you whether things are good or bad, right? And you're trying to collect as much reward as possible. So why is this called a Markov decision process? What makes it Markov? Markov property. What's the Markov property?
Markov property is that we don't care about the past. If we know the current state, we can build them.
That's right. Yeah. So you kind of don't care about the past, which means that your current state is a sufficient statistic of the future, which means your past is independent of your future, conditional on your present. Right? So this is going to be useful in a second, but one easy way to think about the Markov property is you have a joint distribution of states and actions. You can kind of decompose it as the likelihood of the initial state times the likelihood of the initial action given the initial state times the likelihood of the next state, S1, given the initial state, the initial action, and so on, right? So here's an easy way to think about it, which is like think about this, this factor, right? There's nothing going into it. So you're just going to have a P of S naught. Actually, there should be action labels like that. You think of your A label, the only thing that is its parent is S naught. So you're going to have a P of A naught given S naught factor. And you think of the S1 factor, the things that go into it are A naught and S naught, right? And so this is kind of the framework of like a graphical model or a Bayesian network, right? And you're going to say that, like, try to like read it out factor by factor by factor, right? So you're going to say, this is my first factor, this is my second factor, this is my third factor. And I'm going to repeat saying, this is my fourth factor, this is my fifth factor, right? And so you kind of read it out step by step by step. So you can think of this as your initial state distribution, your likelihood of taking an action at the initial state distribution. There's the likelihood of transitioning to the next state, the likelihood of taking the next action, the likelihood of transitioning to the next state, next action, next state, repeat, right? And so essentially what this is if you have if you have a trajectory, right? A trajectory is a sequence of states, actions, rewards. Let's forget about the rewards for a second. If you have a trajectory, which is a sequence of states and actions, this gives you the likelihood of a trajectory. And you can decompose it into P of S naught times P of A naught given S naught times P of S1 given S naught A naught and so on, right? And if you didn't have the Markov property, you couldn't decompose it this way, right? Because you might depend on everything in the past. So this is going to like be useful in the future. But this is what makes it an MDP. Questions? And follow that? Okay, sweet. So the goal of reinforcement learning is for us to learn the parameters of our policy pi theta. And our policy pi theta is going to try and maximize the expected sum of rewards. So we're going to see if we sample trajectories. So trajectories are a sequence of states, actions, and rewards. We sample trajectories from our policy. We're going to try and maximize the expectation over the sum of rewards in any trajectory, right? So we're going to say, hey, I'm going to start from some initial state. I'm going to sample a trajectory. I'm going to sample another trajectory, another trajectory, another trajectory. I'm going to sum up the rewards along each trajectory, and I'm going to average them over many trajectories, right? And so what makes it the expected sum of rewards is you take many different trajectory samples. For each of them, you sum up the rewards, and then you average the rewards over many trajectories, right? Yes? Everyone with me? Okay, so I asked this last time, but why is it an expectation? What makes it necessary to be an expectation rather than average? Or rather than a deterministic entity? What makes it stochastic? You want to remember? Like, why is it an expectation?
Because we have a transition probability from a state 1 to state 2, so
Right.
it's not a uniform distribution. It's
That's
associated with some different.
Or even if it is a uniform distribution, it's still a distribution, right?
Yeah.
And so you have to be probabilistic about it because there's many possible futures that could happen. It's not that you always transition to the same state. Right? Make sense? Okay, so the goal here is to choose the parameters of a policy. A policy is something that's going to take in your state and produce a corresponding action. You can choose the parameters of your policy, which maximize your expected sum of rewards. Yes? Questions? Does that make sense? If it doesn't make sense, the rest of the class isn't going to make sense because it's all about optimizing that objective. Okay, great. So what are policies? Policies are things that map from states to actions, right? So as we said here, policies are just, they can be anything that takes in a state. Some Turing machine that takes in a state produces an action. We're going to choose parameterized policy classes, but they can be really anything. You could even have like a state machine be your policy. It doesn't matter what it is, or it does matter what it is, but it could be like the definition allows it to be anything, right? And so what we're going to try and do is we're going to use learning-based methods. So we want a mapping which goes from your state to your distribution over actions, right? So the mapping can be something like a table. It can be something that is linear. It could be a neural net. It could be a decision tree. All of these are just different parameterizations of a policy, right? Only thing I'm really going to assume is that the policy parameterization is differentiable, right? Like you would take gradients through it. But otherwise, it's just something that maps from states to actions. It's a function that takes in state and produces a distribution over actions as output, right? Make sense? Okay, so what's a distribution over actions? What does that mean? Just a word I made up, right? So what is a distribution over actions? Yeah. Yeah, I guess the policy is producing the distribution over actions, but when I say a distribution over actions, like what types of distributions am I talking about? What do we mean by distribution? Okay, maybe let me keep going. Like a distribution could be something like a Gaussian, right? It could be something like a categorical. It could be a mixture of Gaussians. It could be a diffusion model. But essentially what it's saying is that you have a state going into a function, right? Here's your function. And then you're producing the parameters of a probability distribution, right? So in the Gaussian case, you're going to produce the mean and variance, right? And the Gaussian distribution is fully parameterized by its mean and variance. So like essentially what this gives me is a probability distribution which I can sample from, I can get likelihoods from. There's one over here if you want. There's one over here, there's two over there. But you're trying to take in a state, produce the mean and covariance, right? And this completely determines the probability distribution. And the nice part about it is then if I want to act, I can just take my state, stick it into my function. It gives me a distribution and I can sample from that distribution. So I can like say, gives me a Gaussian, let me draw samples from that distribution, and it's going to be distributed according to the parameters of that distribution. Okay? So its mean is going to be mu, its covariance is going to be sigma. Okay, so Gaussian is the simplest form of a distribution. The next form of distribution is going to be a categorical. So a categorical distribution is just something which is choosing between k discrete choices, right? So it's saying that you have k discrete choices, you want to pick one of them. This is giving you the likelihood that you pick each one of them. Only constraint is that they're positive and that they add up to 1. You can also have things like mixtures of Gaussians, and mixtures of Gaussians are more expressive than Gaussians because you can represent like curves, you can represent probability distributions that look like that rather than just single Gaussians, right? So it's useful when you have many different ways of doing something to have more expressive distributions like mixtures. And then things like diffusion models, you can kind of think of them as infinite mixtures. They're like mixtures which have infinite components. And if you have infinite components, you can represent an infinitely multimodal distribution, right? And so you want to think of a policy as a combination of a mapping type, right? So you want to think of it as a combination of a mapping, whether it's a neural net, a tabular, linear, decision tree, whatever, which maps to the parameters of a distribution. And the complexity of a policy is determined both by the choice of, big neural net, more expressive, small neural net, less expressive. But it's also determined by the complexity of your probability distribution, right? So like a Gaussian can't represent, like a Gaussian is going to struggle to represent something like that. Like it doesn't fit in the policy class. Right? So the important part is like, if I have actions that actually come from here, and I try to fit a Gaussian, it's going to lead to certain problems, right? Because you're like, you cannot fit this with a Gaussian. And so you need a more expressive distribution. Okay. Questions?
When we're choosing what distribution we want to map to, is there a reason why we would always default to the most expressive distribution?
That's a great question. So the question is, why shouldn't we always choose the most expressive distribution? And often, the simplest reason is that it's easier to code the Gaussians, and it's easier to debug, so more efficient. I think the more meaningful reason is perhaps inference speed. So like for something like a diffusion policy or diffusion model, you're gonna represent this score function, and to sample from it, like in a Gaussian, you can just sample from a Gaussian with a random number generator. But to sample from a diffusion policy, you have to follow this forward diffusion process, or reverse diffusion process, right? And so it's like way slower and often a bit harder to train, although it's getting better now. And so I think stability and inference speed are usually the trade-offs that you have. Yeah. Like the loss fluctuates up and down. Yeah. Okay. Great. So everyone with me on policies? Yeah. So the goal, yeah, go ahead.
Are states also be distributions or?
States usually, because you're like observing a state in a Markov process, you're observing the state and we're treating that as a sufficient statistic of the world. Usually in these settings, you treat the states as like points. But if you're in like a POMDP or a partial observed setting, then you have to operate on belief states, which are essentially probability distributions. And so then you would often you'll operate on the sufficient statistics of a state distribution. And so you'd have a policy which doesn't operate on a state, it operates on a distribution of states, but not in the MDP setting. Great question. Okay. Yeah, everyone with me? Good. So, okay, so we said we're going to do this expectation, and we said we're going to do stochastic policies, like we had all of this stuff about distributions, and that's great, right? But there's like an interesting lemma that shows that for all MDPs with deterministic reward and standard assumptions, there exists a deterministic optimal policy, which means that I'm not saying that the only policy is deterministic, but there exists a policy which is not stochastic, which means that it's like at every state, you map to a single action, right? So there exists a policy that is optimal for every single MDP under standard assumptions with deterministic reward. But you can also have optimal policies that are stochastic, right? So an optimal policy is something that is better than every other policy, right? And so in terms of how good its expected sum of rewards is, so in terms of this entity, there will always be policy that is deterministic, but the optimal policy doesn't have to be deterministic, right? And so then the question becomes, why do we even care about stochastic policies if the optimal policy is deterministic? And the reason is that you're trying to explore the world to figure out how the world works. And so the stochasticity is often useful to figure out how the world works or to explore the world. And so it helps in the search or optimization process, but often in practice, and you'll do this in your homeworks too, you like optimize a stochastic policy. And then when you're deploying it, you'll just kill all the noise. And so you like use the stochastic policy to do search, you'll use it to do optimization. And then like, for instance, in a Gaussian, you'll set the covariance to 0 when you're running it. So you'll run a deterministic policy. Yeah, the lemma is a bit out of scope, but just look at it. The point here is that stochastic policies are useful to explore the world, but oftentimes the way you can act can be deterministic. You don't have to be random in the way that you act. Okay. So that's about policies. Do policies make sense to everyone? Okay. So policies, the goal of policies is to maximize the expected sum of rewards. But I've like kind of used this expectation a bit loosely, right? So I just want to get into what I mean by an expectation a little more formally, right? So there's two types of models we can consider. One is finite horizon, and one is infinite horizon, right? So finite horizon means that you're taking the sum of rewards from time step 0 to time step t, right? And infinite horizon is saying you're taking the sum from 0 to infinity, right? And so let's start by looking at finite horizon. So finite horizon is saying you can take the sum from 0 to t, but the interesting thing about finite horizon policies is that they're non-stationary, which means that if I get to a state with 2 steps remaining versus get to a state with 50 steps remaining, the way I act will be different, right? So here's an example. I'm playing a board game and, I'm like 5 steps out from the end versus I'm 50 steps out from the end. Oh shit, I forgot to record. Oh no, I got it. I'm 5 steps out from the end versus 50 steps out from the end. Like the way that I act will be different. Okay? Like the strategies that I can play when I have lots of time left versus no time left are not the same strategy. And so, at least in single agent MDPs, often you want to choose, you have finite horizon MDPs having non-stationary solutions, which means that your policy can't just take in a state and give you an action. Instead, your policy has to take in state and time and give you an action. Right? And so the important bit is that if you're in the finite horizon, if you're being like completely proper about it, you need to know how much time you have left. And how much time you have left determines how you behave. Right? And so the point is, in the finite horizon, you need to include time as part of your state. So like it's easy fix, but all you need to do is include time as part of your state. Okay, but often what we do is we say fuck it and we just ignore the time. And so in practice, you'll often ignore the time and you'll just have a policy that takes in state and produces distribution over actions. Okay, so what happens if we just apply this objective, this one up here, to an infinite horizon? Does that work? Yeah. Yeah, that's right. That's right. It just blows up, right? If you have rewards. Sorry. Okay, yeah. If you have rewards that are sorry guys, my computer is misbehaving. Okay, so if you have things that are okay, sweet. If you have things that are infinite horizon, if you just add up a bunch of positive numbers, for many series, it's going to diverge, not for all, right? And so often what you do in an infinite horizon case, you choose a discounted sum of rewards, which means that as you get rewards further in the future, you discount them, as in you weigh them less and less and less, right? Which means that if you have rewards 3 steps in the future, you're going to weigh them by gamma to the 3. And so gamma is going to be a number between 0 and 1. But the point here is There's some seats here, Helen. You don't have to, but yeah. If you have, something 3 steps in the future, you're going to weight by gamma to the 3. And if gamma is a number less than 1, then it's going to be weighed less and less and less and less, right? So you have this exponentially discounted sum of rewards. And so intuitively, it just means that you like value things that you get earlier, bet more, and value things that you get later, less. There's also like more complicated ways to explain it, but that's the simplest way. You just want to be greedy in the sense you want to just get the reward ASAP. Yeah. And so often, like in a lot of, I'm going to be a little loose in this class about infinite versus finite horizon. So don't read into it too much. But if you ever want to think about it, think about finite horizon as non-stationary, which means your policy depends on time. Infinite horizon is stationary. Policy doesn't depend on time, but you have to discount.
In this type of setting, do you always assume that the rewards at each time step are equally like reliable? There are situations where early on the rewards are very unreliable.
Yeah.
Later on they're better.
In all of these settings, we're assuming that the reward is deterministic, and we're assuming that it's always correct. But I think when you can also do settings with stochastic reward, and in that case, you have to estimate the reliability of your reward. And so that's like a bit of a different setting, but here we're assuming rewards are perfectly reliable.
So for infinite horizon, if we're valuing the earlier steps a lot more than the later steps, wouldn't the policy learn to value the early steps more as well?
Yeah. So the policy, like, it's kind of like a choice saying that your your gamma is usually pretty close to 1. So it's like 0.99. So it's not greedy. It's not like 1 step drop off, but there's some k step drop off. And so that's kind of like a choice of the algorithm designer to see how much do you want to value the future versus thought.
I might be misunderstanding how non-stationary versus stationary works, because wouldn't that mean like our decisions still very dependent based on the number of steps we're at?
No, because you always have infinite steps in the future. Right? So it's like you're always summing to infinity. And so like basically, whether I encounter this state now or later, I'm always going to have infinite steps in the future. Right? So this objective, starting from a particular state, will be kind of the same, like no matter whether I encountered it now or later. Right? So if I encounter the state again, it's going to be the same. That question. Yeah.
Okay, so let's say you like value the final state more than the earlier states. Would that come into the way your discount factor is zoned, or would you disrupt your priority?
So it depends what you mean by final state. If it's like you get reward at the 100th time step, no matter what, then then it has to be some time dependent entity, which means that your policy has to be time dependent, right? If it's always that like when I complete the task, I get a reward, then it goes into your reward function and not into your time steps. And so it kind of depends what you mean by final, right? So it's like if I can always run for 100 steps and I reward the end, that's a non-stationary finite horizon setting, and otherwise it's the infinite horizon.
But why did you say that not including T as part of the state space is okay, or generally it's something like that?
It's largely an empirical thing, like as in we just do it and it's fine. I think the reason often is that if you have lots of states with lots of trajectories with loops, right, then you come back to the same state again, and then you have to behave a certain way. But lots of the tasks that we consider, especially in robotics, you don't always have loops. And so you're never coming back to the same state, it kind of doesn't matter. So that's usually what makes it okay. Yeah.
Okay, bro. Let's go with the policy perform better if we took Q into account as well.
Yes and no. Like I think not having the T kind of reduces data share, because you can like if you haven't seen like it doesn't allow you to share data between instances of the state at different times. But if you so there's like you're obviously choosing a wrong parameterization by removing T, but it allows for better data sharing. So there's like a bit of a trade-off when it comes to function approximation. Okay. So that's infinite versus finite horizon. Okay. So the other thing that I kind of glossed over is this expectation. And And so we've been saying there's this expected sum of rewards in the trajectory. Like what I mean by this expectation, let's kind of unpack it, right? Like this is like kind of shorthand, and I'll use the shorthand, but let's kind of go into the details of what trajectory sampling means, right? So usually sampling a trajectory is this process you call ancestral sampling, right? Which means just like sampling time step by time step by time, which means that you're going to sample the first step, the first state from the initial state distribution. Then you will sample the next action, the first action from the policy pi theta. Then you will sample the first time step from the transition dynamics. Then you will sample the next action from the policy, the next state from the transition dynamics, and you keep repeating, right? And so the way that you like instantiate this in code is that you like run what you call a rollout, right? And a rollout is basically you start by resetting the world to some state from your initial state distribution, right? You reset it to say like all the objects are on the table. And then you pick your first action by running it through your policy. You have this function, your policy. You run your state through your policy, gives you an action, right? And then you execute the action in the world. So you can think of the transition dynamics as just executing the actions in the world. So if you have a robot, your policy says move up, you execute the process of moving up. The world transitions to a new state, and then you query your policy again. Your policy gives you a new action to take, right? You repeat taking that action. The world transitions to a new state and you repeat, right? So you keep going on and on and on. So the way you run this in code is you just have a for loop, and in each for loop, you get the observations from the world, you run it through your policy, you're going to get an action, you play the action, go to a new state, repeat, right? And so that's what you're going to call a rollout. And you can run that for infinite horizons. So you start with initial state, you go through your policy, go through your dynamics, your policy, your dynamics, repeat, right? Does that make sense? So just think of this, that trajectory thing is a shorthand for this thing, right? This thing is just saying state, action, state, action, state, action, state, action, right? And every step you're going to get reward based on what state you're in. And then an intermediate compact thing that I often use, I'm going to use in the notation, is you're going to sample your initial state from your initial state distribution. You're going to sample AT from pi theta given ST, and ST plus 1 from your transition dynamics, right? So this is, when I use the shorthand, I mean, I'm going to like, it assumes that you're taking multiple steps of initial state, policy dynamics, policy dynamics, policy dynamics, repeat. Right? So just like, think of it as like I drew earlier, you start from an initial state, you take a bunch of rollouts, right? So you choose an action, you transition, you take your next state, you choose an action, you transition, choose an action, transition, right? You just repeat this process. Okay, so that's the most like standard way of representing this expectation. There's a slightly more complicated way of like expressing it, which we'll use sometimes, but I think it's kind of interesting to know, which is when you're in the infinite horizon setting. Sorry, my computer's acting up. Okay, when you're in infinite horizon setting, you can kind of view this through the lens of a stationary distribution. How many of you know what a stationary distribution is? No? Yes? Okay. So here's one way of thinking about it. Like, let's say we started at a state S0, right? And you had a trajectory. And let's say you like encountered state A, B, C, A, right? And then you took another trajectory and you encountered B, C, D, E, right? And you took another thing and you encountered E, A, B, G. Okay, I'm making these up. But the point is that one way of computing the expected sum of rewards is to add up the rewards along each of these, right? Add up the rewards along every trajectory and then average all the trajectories, right? The other thing that you can do is you can find out what is the likelihood of visiting a state and taking an action, right? So you can say, okay, like here, if I look at a histogram of A, B, C, D, E, G, right? I visited A 3 times, and I visited B 3 times, and I visited C 2 times, and I visited D 1 time, and E 1 time, and whatever, right? So you can like take a histogram of all the things that you visited on average, right? And then you can like sum up the rewards weighted by how likely you were to encounter a state, right? So you can think of, if I want to get the average sum of rewards, one of them is to add up this way, and then average this way, right? The other one is to like figure out what the average likelihood of ending up at a state was, and then average the sum of rewards according to that likelihood. So it's basically saying that if I took these trajectories and I had like a, 30% chance of ending up on A, and like 30% chance of ending up on B, and a 10% chance of ending up on C, 10% on G, right? I can take the reward, I can like basically take the reward of A and multiply it by 30%, and take the reward of B, multiply it by 30%, take the reward of C, multiply it by 10%, and repeat, right? And so essentially, if I can figure out what the likelihood is of ending up at a particular state, and I like average that over all, if I like compute that over all the states, then to get the average value of a policy, you say, okay, if I run this policy, how likely am I to be in A? How likely am I to be in B, C, D, E, F, G over all the states? And then you compute, then you multiply that times reward and average it, right? So it's saying like, the difference is saying one of them is computing rewards and averaging. The other one is computing how likely am I to visit a state, and then saying like, to get the average reward, I'm going to take the reward of the state by how likely I am to be in that state and average. Okay, it's a little bit confusing, but ask me questions. Which part of that doesn't make sense? Yeah.
What if you had like a lot of things?
Yeah, yeah. That's a great question. So if you have a lot of states, this becomes hard, right? And so what I did is I wrote it as like a discrete thing where there's like 10 states. It's obviously hard to compute that, but there's like techniques that we'll cover later in the class of like computing this through like optimization. So you can compute it as like a Gaussian distribution or a diffusion model or something. And then the way to compute this expectation, so when you have a stationary distribution, the way to compute this expectation is not to enumerate all the states, but is to sample from this distribution a bunch of times and like average it, right? So it's saying that like, if I have this distribution and A is likely 30%, if I sample from it, like 30% of the things are likely to be A, right? And so essentially the way you compute these expectations is not to enumerate all the states and add them, it's to like sample from it and average, right? So it doesn't matter if you don't get this that well right now. The point here is just think of it as two different ways of computing the same thing.
How is the ancestral sampling? Is that similar to game sampling or is it?
I guess Git sampling is more like you like keep all the variables except for one the same, right? And you split it. Ancestral sampling is more like if I have like a chain, right? It's like I sample from this thing first, and then I sample from this thing conditioned on this thing, then sample from this thing conditioned on this thing, right? So it's like more like sampling in a chain. So it's like in MCMC, like I'm guessing you're coming from MCMC and that kind of world, like that world, it's like if you're running an MCMC chain, it's like from time step to time step. It's kind of like ancestral sampling. Like you sample one time step, you go to the next, to the next, to the next. Yeah.
You always sample, I guess, all of the time steps between the current time step and the time step.
Yeah.
Like if there's like a million, right?
Yeah.
Steps, but like very.
Yeah. So what you can often do is that you like approximate when you have a discount, you approximate it because like let's say you have 0.9 or something, within like 10 to 20 steps it becomes negligibly small, and so you like start to ignore it after. So your discount lets you like truncate your horizon to be months. Okay. So honestly, yeah, go ahead. Why is it called mu? Oh, because it's when you run a Markov chain, right? Like when it converges, it like doesn't change, as in the thing is in a like what goes in comes out, and so it's like in this stationary balance. So you're in some distribution, all the stuff that goes in comes out. That's why it's called stationary. Yeah.
I have a question now, because for some Markov chains, there isn't a actual stationary distribution at the very end.
That's right.
So if that happens, then how do you calculate it?
We're gonna like assume that the Markov chains are ergodic and basically aperiodic, and that like lets them converge, right? And so we ignore the case that you're talking about. Yeah.
Question about the equation for the stationary.
Yes. Well, I
So-
haven't gone through it yet.
Oh.
Maybe I should go through it.
Okay. sure.
Okay, yeah. So the way that you can think about a stationary distribution is like this thingy, this mumbo jumbo of numbers and symbols is just saying what is the likelihood that at time step t your state was S and your action was A, right? So it's like saying it's like the same way of saying like what is the likelihood of reaching state A, state B, state C? This is saying that at time step t, what is the likelihood that you started from your initial state distribution, you ran your policy, you're under your state dynamics, and you reached state S and took action A, right? So what is the likelihood of getting to a state S, taking an action A at a particular time step? Okay. Then the mu is saying, let's average that over all the time steps, right? Because you can be at that state at any time step. And so we're going to average that over all the time steps with discount because you're going to do an infinite horizon thing. And then once you have your mu, then you can say that this objective on the left in the infinite horizon with like a little gamma on it is equal to this objective on the right. That could be a little piece of homework for the more mathematically inclined, but essentially what this is saying is this is the likelihood I got to some state at time step t and took the action A. This is saying what is the likelihood this happened averaged over all possible time steps? Like it doesn't matter, or it does matter, but like did I get to time step A at the first time step or the third time step or the fifth time step? So you want to average over all, right? And then this is saying, this is giving me basically what is the likelihood of showing up at state S taking action A at any time step? And then I average reward weighted by that distribution to get the value of a policy. Yeah.
That much, given that it is infinite.
It does matter because our objective is not an unweighted one. And so an occurrence at 5 steps in the future is different from an occurrence at 1 step in the future. That's why you weight this by again. Yeah.
So it shouldn't go to multiplied by 1.
Oh, it's so that because if you have an infinite horizon geometric series, it becomes 1 over 1 minus gamma. And so this is to make sure that your probability distribution integrates to 1. Because when you weight it by gamma, it may not be a probability distribution. So it's just to make sure that it integrates. Okay, so the good news is that we're not going to use stationary distributions for the next 5 lectures. And so the main thing you guys need to keep in mind is the ancestral view of sampling, state, action, next state, action, next state. But I think stationary distributions are cool. And so they're fun to learn about. Okay. Everyone kind of with me so far? Yeah, go ahead.
I still have clarification.
Yes.
Question.
Yes.
So for the top equation of stationary view, in Markov process, we don't care about what happened in the past, right? So why do we still take all the steps from the initial step up to t?
Oh, because those are in the future, right? Like it's saying that like this is the likelihood of starting from some initial state and then getting to a particular state at t in the future.
I see, okay.
Great questions. Okay, so let's keep going. So where does deep learning fit into all of this, right? We're all deep learners at the end of the day. And so where does deep learning fit in? The way we represent things like our policies or our state distributions are often, or these things called Q and V, Q values and value functions, which we'll cover in a couple of lectures. They're all represented by deep neural networks often. And representing them with deep neural networks is an opportunity because they're generalized. You can get them to work from perception. They can incorporate prior knowledge, things like that. But it causes lots of problems, right? So it's going to make convergence hard. It's going to make the theoretical properties more murky. It's going to cause all sorts of trouble. And so the study of deep reinforcement learning, deep RL, is like all about how do we tame the combination of function approximation with this like theoretical framework of reinforcement learning. Okay? So reinforcement learning is well studied, kind of explained well, but when combining it with neural networks, relatively less understood. And so that's kind of the space that I operate in often. Okay, so why is it important now? I think we've got better algorithms, we've got more data, and hopefully we have more compute, right? And so the hope is that just like every other field of machine learning, A combination of better algorithms, more data, and more compute should lead to more performant RL algorithms. I'd say like we're maybe like 10 years behind every other field in deep RL, but it's an opportunity to do great research. Okay, so that's kind of why we should care. I'm gonna skip a bunch of this so that we can get to imitation learning. But I think one thing to remember about deep RL methods is that they're nice because they can solve sequential decision-making problems. They enable you to keep getting better over time. Potentially applicable to things that are hard to model with contact physics and so on, or analytically model. And the hope is that, you know, we don't have to sit and collect data all the time, but we can keep getting better. Yeah.
From like a practical point of view, if you like parameterize your policy with like some neural network, to take like gradient stuff with respect to your reward, not sampling like new actions that keep pointing trajectory, like what's the common practice people have to get around this stuff? Or to approximate the sampling procedure?
Yeah.
Saving gradients. Like,
Yeah. That's going to be like the next 4 lectures.
Okay.
But basically, the tricky part is that you don't know the transition dynamics. And so if you don't know the transition dynamics, you can't take gradients through them. And so what you have to often do is you have to like approximate the gradients through your transition dynamics. And so like that's kind of what policy gradient and these kinds of things do. There's also like things like model-based RL, which try to approximate your dynamics with a differentiable surrogate and then take gradients through the whole thing. And so the whole class is really about how do we approximate the actions. Yeah, that's a great question. But I think there's lots of different ways to approximate it. It's just like which approximation suits your problem best. Yeah. Sweet. Okay, so let's skip past the applications a little bit. So it helps in a bunch of stuff. Okay, yeah. So for those of you who are practitioners, here's where you shouldn't use reinforcement learning, which is in things that are safety critical and repetitive, right? So like, I wouldn't use reinforcement learning on your surgery robots or on a spacecraft. Like that's probably not the right move, in my opinion. Just because they're like often well modeled, at least the spacecraft and factory settings. And they're like safety critical in a way that it's hard to provide guarantees for these reinforcement learning with function approximation type methods. And they're often repetitive, like you're doing the same thing over and over and over. And so in those cases, things like iterative learning control or model predictive control are often more effective. But in other settings, reinforcement learning is better. Yeah.
Do you add constraints on your action pairs to add safety?
You can, yeah. So there's like a field of safe reinforcement learning. The tricky part is it's like you have to balance exploration and exploitation. So you don't know the world. So you have to take some actions outside of what you know, but you need to make sure that they're safe. And so that's what makes it kind of tricky to do reinforcement learning with safety. Yeah.
Are the results for are well understood?
Like linear, tabular. There's like a class of methods called bilinear classes, like which are like essentially bilinear functions, like things that are functions of state, linearly multiplied with functions of action. And so there's like some set of problems like that, but general nonlinear dynamics not well understood. Okay, so where is reinforcement learning useful? I think domains which have lots of diversity, but potentially cheap data collection. So things like robotics, I think is promising, but you have to be careful about how you collect the data. You can't just like let your robot run amok in your house. I wouldn't recommend that. But there's other domains like games, certain types of educational platforms, LLMs in a certain way, science, right? So there's other applications where it's useful, but not things that are repetitive or extremely safety critical. I think those are hard. Yeah. Sweet. Okay. So far I've equated sequential decision making to reinforcement learning, but sequential decision making is much bigger as a field than reinforcement learning. Reinforcement learning is a solution technique to sequential decision making problems, right? So a lot of what we've talked about so far is not really reinforcement learning. It's just the formalism of sequential decision making. Reinforcement learning is doing sequential decision making under a certain set of assumptions, right? So the assumptions are that you only have sampling access to the environment, so you don't know what the dynamics are. You can just sample it. You just like take steps in it. You're given a reward function, and you're trying to do some sort of goal-directed behavior. So you're trying to be rational in some capacity, right? So you're trying to maximize some utility. And so those are the typical assumptions of reinforcement learning. There's other ways of solving sequential decision-making problems, right? So there's things like trajectory optimization. So trajectory optimization is often with known dynamics. So like, for instance, a lot of you who work on control, like would solve trajectory optimization problems where you have a model, it's maybe non-convex, and you're trying to like find optimization techniques that kind of work well in those settings, but the model is known and you can kind of take gradients through it. But in reinforcement learning, you often just assume black box sampling access to the environment. You don't assume things about like convexity of your dynamics and so on.
Is limited to relatively.
Imitation learning is something lots of you have probably heard about, and we should cover soon. But it's basically not learning through trial and error experience, but instead learning from experts who might demonstrate behavior to you, right? And so here are some examples from TRI where they demonstrate all of these expert behaviors and have the agents kind of copy them. And then you can have things like learning world models or unsupervised decision-making, where you say, I'm going to take a large corpus of the internet, right, or of video data and kind of learn how the world works and then plan with it. Like, I think one of you asked a question about Jan's take on MPC on ed. Basically, unsupervised decision-making is the process of learning how the world works and then acting. This is often we'd call it model-based reinforcement learning, but it's kind of in the realm of things that is a little different than just maximizing the reward, right? There's lots of different ways to solve this problem. There's more ways than this too, but I just want to emphasize that sequential decision-making is not just RL. RL is a solution to a sequential decision-making problem, right? Under a certain set of assumptions. Okay, so now we get to our class structure. We'll start with imitation learning, right? Which is the easiest thing to think about. It'll be what your first homework's on. We'll then get to model-free reinforcement learning. We'll cover two types of techniques, policy gradient and approximate dynamic programming, things that you'd call Q learning, active-critic, things like that. We'll next cover model-based reinforcement learning, right? So things where you try to learn the transition dynamics of the world and use that for straight through gradient estimation or gradient estimation with differentiable surrogates. We'll try and connect these two things, right? So model-based RL is kind of like learning how the world works. This is learning how to act in the world. We'll show that these are approximations to the same objective, right? So we'll try and connect these two. And then we'll do some frontiers. So we'll study things like exploration, learning from prior data or offline reinforcement learning, learning across tasks. And if we have time, we'll study multi-agent RL a little bit. And RL with large models, so like diffusion models and transformers and so on. So those will all be in frontiers, right? Depends how fast we go. Okay, so do you all prefer I go faster, go slower? What's the pace that you prefer? I generally tend to go reasonably slow so everyone gets it. Otherwise, it'll lead to confusion. But if you ever feel like I should go faster, just tell me. Okay, good. So that's the first section. Any questions before we keep going? Yeah.
Or would it not be?
So I think, I think maybe that statement needs to be qualified a little bit in the sense that if I can model the world, if I'm going to do the same thing 10,000 times, if I spend some human effort modeling the world, potentially that is safer, more repeatable, and you solve it with planning better than reinforcement learning. If it's hard for me to model the world, for instance, in crocheting, it's kind of hard to model the world. In those settings, reinforcement learning is potentially really useful. But it's like if a factory, you're doing pick and place, like reinforcement learning is not the right choice.
Like,
Yeah, something that's easy to model. Okay, great. Sweet. So let's start with imitation learning. So what is imitation learning? This is an example I stole from my student K. Oh man, what's going on with this? It's like lagging a lot. Okay, but the point is, it's Sai teaching someone how to do the Gangnam style. And there's lots of tasks like this that we learn from imitation or we learn from observation. And things that are like, I know I can't do this, but things that are often non-trivial are often learned from observation. So, so the premise of imitation learning is often there's an expert whose brain you don't have access to, right? So if I had your brain, then it would be fine, but I don't have your brain. I just see expert traces of behavior, like someone is showing me what optimal looks like, and then I try to figure out what optimal means and copy it in a way that's generalizable to new situations. And so the premise of imitation learning is learning from experts in a way that's generalizable, right? So the premise is you're given demonstrations of optimal behavior. So that means you're given states and actions. So S naught I, A naught I, S1I, A1I, till STI, ATI. Given n of them, right? And they're assumed to be optimal or noisily optimal, right? Which means that they're like little wiggles around optimal. So that's what you're given. And what you need to do is you need to use that optimal behavior to kind of train a policy, right? So policy phi theta, which is going to take in a state, produce an action A, in order to mimic that behavior. Right? So imitation learning is really about taking that data. You're given nothing else. You're just given that data set of SA, 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 SA. The assumption is that it's close to optimal. You're trying to learn a policy that mimics the demonstrator, right? Okay. So essentially what you're going to try and do, this is a case from autonomous driving, is you're going to try and take this data, you're going to try and use it to set the parameters of a policy, which is going to figure out how to drive. And so autonomous driving is a great case where you have lots of expert data or close to expert data, and you try and imitate that expert data to figure out how to drive. Right. So the pros here is that you don't need rewards. Right. So we talked about rewards and sequential decision-making, exploration. You don't need any of that. Someone has given you expert optimal behavior, right? And so you don't need online experience, you don't need rewards, but you have to figure out a policy phi theta that generalizes to new settings. Okay, so if you were to do this, how do we do this? What's the simplest way to take close to optimal data and get a policy that is close to optimal? Supervised learning, that's it. Right, so sorry, my computer's lagging a lot today. So the idea behind the easiest way to do imitation learning, which we call behavior cloning, is to treat imitation learning as a supervised learning problem. Right? How many folks are familiar with supervised learning? Okay, most people, yeah. So supervised learning is just saying you're going to take XY pairs, you're going to treat them as optimal, and you're just going to do what you call maximum likelihood. So you try to pick the parameters of a policy which maximize the likelihood of producing expert labels given those states. Right? And so you're going to treat this as a regression problem or a classification problem. But essentially, you're going to solve this maximum likelihood problem, which says that given states and actions, which we assume to be optimal from the demonstrators, right? This is optimal. You try to choose the parameters of a policy. Remember, this is a probability distribution, right? Phi theta is a probability distribution. You're going to try and choose the parameters theta of your policy, which maximize the likelihood of producing A star when the policy is fed S star. Right? So essentially, this is like, if you think about how people do like classification or regression, this is exactly the same objective. In classification, you're going to take like argmax theta, you're going to have like X and Y. You're going to have log pi or log B of Y given X. Right? So you often figure out Y. And depending on your choice of what P theta is going to be, you'll come up with different loss functions. Right? So if you choose P theta to be a categorical distribution, you'll get cross entropy. If you choose P theta to be a Gaussian, you'll get mean squared error. And we'll discuss that in a second. But essentially, almost all supervised learning in some way is maximum likelihood. Right? You're trying to choose the parameters theta that maximize the likelihood of producing actions A star when you feed in states S star. Right? That's it. Okay, so what you're going to do is you're going to take all of your states and actions, you're going to mush them up, right? So you're going to like ignore their sequential nature. You're going to mush them up into replay buffer, right? You're going to like, the way you're going to implement this is you're going to like mush it into replay buffer, randomly shuffle them, right? And then do like supervised learning. And so essentially, it's kind of the same thing that you do for classification. You're just going to like treat sequential decision making as a classification problem or a regression problem. You're just going to do maximum likelihood, right? And so that's gonna go into your supervised learning. It'll give you a policy phi theta. Phi theta is what you use to act in the world, right? And so it's essentially an offline process. You're going to take in your data set. Your data set's going to go through this like big optimization thingy. It's going to spit out theta. Theta is going to act in the world, all offline. So you don't do any online optimization. There's no reinforcement learning. Data goes into like big GPU spits out theta. Theta goes and acts in the world. That's it, right? So that's all that behavior cloning is. Any questions? Okay. So the important things to remember is that you're going to like ignore the sequential nature of the problem. So you're going to take states and actions, mush them up together, take it into a replay buffer and treat them as IID samples, right? And then you're just going to do maximum likelihood, supervised learning. Okay. So the way you're going to like implement this in code is just like really, don't copy this for your homework, but ignore this. But essentially, it's super easy in that you're just going to get your states, your actions, and then you're just going to get like a target distribution, and then just do like some loss function, which is your mean squared error, your cross entropy loss. You literally treat it like a classification problem, right? It's like that easy. It's very, very short. And the like art of behavior cloning is often in choosing the right policy architecture, or curating your data and things like that, right? But the core algorithm is just that, right? Just supervised learning. Okay, everyone with me? So the point here is that you can use different policy classes. So you can use different policy classes like tabular, linear, or like neural nets. Again, it just has to be differentiable, right? Anything that allows you to solve that maximum likelihood problem. You can solve that maximum likelihood problem with random search if you want. The easiest way to do it is with gradients, but you can solve it with whatever you really want, right? And all of that would come under behavior cloning. So often you're going to choose a different choice of function approximator, and you might choose a different choice of like policy class. We'll get into that, right? But the first occurrence that I can think of was proposed in 1988 or 89. It's called Alvin, but I think it was at CMU. They were trying to do autonomous navigation with this car, and the input looked something like that. And it went through a perceptron, and the perceptron outputted like whether to go left or right. So it's like not that different than what we do today, which is a little sad, but it's kind of cool that it works in 1989. And they like drove around the CMU campus and other places, which was cool. What it looks like today, this is from some folks in Stanford, and they like have demonstrations that look something like that. And then they have an autonomous system kind of replicate that behavior, potentially in slightly different settings, right? So that's autonomous. You can see that it looks kind of cool, right? Like the nice part about behavior cloning is that you don't have to fight exploration, you don't have to fight safety, you don't like a human is just giving it to you. It's an offline process, it's simple. But there's going to be flaws, as we'll talk about. But you can get pretty cool behavior. If you've seen any of the stuff from 1X or Figure, like all of it is essentially using some version of behavior cloning. But essentially supervised learning with like a rich, powerful model that goes from perception. Yes. Sometimes. I think it's like not super well understood when they generalize, but I'll say that they generalize better than we'd expect, but not all the time. And so the reason we want to do RL and other things like that is because behavior cloning doesn't generalize well enough. Right? And so, yeah. Okay, so yes. Go ahead.
So when we're doing invitation learning, we shuffle like all the data and then treat them as if they're independent events.
That's right.
But in like reality, when you're trying to imitate human action,
Right.
different actions are actually based on.
Yeah, so one thing that makes it okay to do that is because you're assuming it's a Markov system, Right? So if it's a Markov system and your demonstrators are truly Markov, then this works fine. Right? Like you don't need access to history to take optimal decisions. Right? So the thing that makes it okay is it's a Markov system. If it's a Markov system, the problem is that lots of systems are not truly Markov. The second thing that's a little tricky is that humans are not Markov. And so like often, like for instance, if I like paused, so if I like move somewhere, I pause and I keep going, like that's not a Markovian behavior, because at the same state, I sometimes paused and I sometimes didn't pause. Right. So it's like not obvious how to act. And so the tricky part comes when you like the behavior cloning algorithm assumes Markov, but if you feed in non-Markov data to it, then it becomes a mess.
Just related to that, I guess this is a thing that exists, like, by the when human demonstrators, like, if you describe a task, you could have it being solved in simulation, and then.
Yeah, so some folks do it in simulation too, but the fundamental issues are often related. Depends how it doesn't need to be a human, it just needs to be an oracle. Okay. Like people do it in language model world too. So it's different, yeah. It's not different, it's kind of the same. Okay, so the key issue with behavior cloning or doing imitation learning to supervised learning is that imitation learning is not supervised learning. You're in a sequential decision-making problem. And so you have this problem, which you're going to call compounding error. How many of you has anyone heard of compounding error? Yes. Okay. So the idea of compounding error is super simple. It's like saying, let's say that I'm a little colorblind, so I can't tell the difference between these colors, but this one is your expert, right? And so you're trying to copy the expert. And so you're saying, I want to copy the expert. And I'm going to like treat this like a supervised learning problem, right? So I'm going to say, okay, at this state, I'm going to take this action, and this state, I'm going to take this action, this state, I'm going to take this action, and so on, right? It's really like a supervised learning problem. And now what's going to happen is that supervised learning problems are not going to have zero error, right? Especially in new states. So it'll have like a tiny bit of error. So what'll happen is that you'll be here, you'll make a tiny little mistake, okay? Or maybe to match this, you'll make a tiny little mistake off this way, yeah? So it's fine because the error is really small, but you're going to make a tiny little mistake. And when you make a tiny little mistake, you go a little bit out of distribution of your training set, right? So your training set was like this thing, okay? So let's take the extreme case where your training set was one trajectory. You make a little mistake, you go a little bit out of distribution. Now I'm a little bit out of distribution, and we know that machine learning kind of struggles out of distribution. So this thing is now being fed an out of distribution state, right? So it's fed an out of distribution state, which means I've seen this state, but I've never seen this state, right? And so if I'm seeing something a little out of distribution, it's going to make a bigger mistake, right? So I'm going to be here, I'm going to make a bigger mistake, and then I'm more out of distribution. And then I'm going to make a bigger mistake, and then I'm going to be more out of distribution, right? So you can kind of see, this is like really easy to replicate. You should replicate in your homework. But essentially, if you have a sequential decision-making problem, if it is a one-step problem, this would be fine, right? Because you took one step, it had a little error, that's okay. But if you take it for like 50 steps, the error will increase over every time step because you'll go a little more out of distribution, you'll make a bigger mistake, a little more out of distribution, bigger mistake, repeat, right? So even if you started off in the same initial state, you'll sometimes see that it like deviates way off, right? So the problem with imitation learning and for like those interested in language models, DPO, it's kind of the same problem, right? Is that you have compounding error, right? So you have compounding error in that you're treating a sequential problem like a non-sequential problem. You're treating it like an IID problem. And so essentially you're really trying to optimize an objective like this, which says I'm going to sample states and actions from my stationary distribution, and I want to match the expert. But you're optimizing an objective like this, which is saying you're going to sample states and actions from your data distribution, right? So these are not the same thing. So the important thing is this is offline, right? The expectation is under your data distribution. This is online. Your expectation is under your policy. And so the way that this manifests is that this is saying, hey, you'll be good on the training set, and that's what your objective is. But when you roll out the policy, you're really sampling sequentially from your policy, right? And so being good on this objective does not mean you're good at this objective, right? And the easiest way to understand it is you make a little mistake, little mistake, little mistake. You read parts of the state space that are not seen in your expert data, and you keep making bigger and bigger and bigger mistakes. Does that make sense? So the key issue comes from taking a sequential problem and then pretending it's a non-sequential problem, right? So pretending it's an IID problem where states and actions come IID from the expert. Yeah. So that's kind of the fundamental issue in behavior cloning. Anytime you do this IID supervised learning thing, it always has this issue, right? So here are some examples of it failing. So you can see that it kind of like drives off the road sometimes. On the right-hand side, you can see, this video plays. But these are some videos from our group where you can see that behavior cloning. Sorry, but behavior cloning basically doesn't work. Doesn't work in scenarios where the system is perturbed, right? Or doesn't work for really long horizon problems because you start seeing compounding error over. Okay, so let's try and understand like how bad this is, right? So what we want to do is we're going to fix it, but let's try and analyze how bad it is a little bit before fixing it. Any questions about this issue before moving on? Okay, so often the goal of imitation learning is you don't have a reward or anything, so you're just trying to match the expert, right? So you're saying that like, if I acted the same way as an expert would have acted, I'm going to get a cost of 0. If I'm acting otherwise, I'm going to get a cost of 1. Right? You're trying to minimize your cost. So we're just going to, the next 2 slides, we're just going to try and analyze the complexity or like how bad imitation learning is. We don't have to use this anyway, just kind of get the intuition of how bad imitation learning is. Right? So we're going to say 0 if you match the expert, 1 otherwise. We want to see how bad imitation learning is in terms of cost incurred, right? And so here's a visualization I find useful. It's kind of like walking a tightrope, right? So you're saying that like, if I was on the tightrope, I know what to do. If I fall off the tightrope, I have no idea what to do, right? Because I've gone out of distribution. I don't know what to deal with. I'm going to go like fall off the cliff and be horribly bad, right? And so a worst case analysis kind of looks like, let's say the policy has an epsilon chance of making an error, right? So which means that you have an epsilon probability of not producing the expert action, right? What we're going to show is that the error compounds quadratically, right? So I'll go through this in a second, but really all we want to show is that this is like walking a tightrope and you're going to get quadratically bad error. And quadratic is bad. You always want subquadratic, right? So what it's saying is that you're going to incur error which grows with horizon, right? So it's going to grow with how wrong your policy is, and it's going to grow with horizon. And together, that's going to make things really bad because as you go to longer and longer and longer horizons, you have quadratically high error. And if you have more and more data, basically your epsilon is going to get larger, which is going to make your policy worse. Right? And so I'll step through this in a second, but the intuition here is we just want to figure out that imitation learning has behavior cloning has quadratically bad error. Okay. So let's does the intuition make sense? Right? So let's kind of step through how we derive this. Right? Super easy. We're going to say you have epsilon chance of making an error at any time step. That's an epsilon chance that you're not going to take what the expert took. Okay. And you have a horizon of h. Let's say you have like 8 steps in your trajectory. You want to like execute your policy for 8 steps. So what you're going to do is this visualization says that let's say you started here. You have an epsilon chance of like going off and 1 minus epsilon of staying on, right? And so what that means is that you're going to have an epsilon chance of like going off here. And if you go off, you're out of distribution and you're just going to be bad. You fell off the tightrope. And so you're going to be bad for the rest of time. Right? So this is a pretty pessimistic bound, so don't take it too serious. But if you're going to fall off the tightrope, you'll be bad for 8 steps in the future. Right? So you're going to say you have an epsilon chance of falling off the tightrope. And once you have fallen off the tightrope, you incur error for every time step in the future because you've fallen off and you don't know how to get back. Right? So you're going to have epsilon h. Right? So per time step, you're going to have epsilon h. And you have a chance of falling off the tightrope at every single step. Right? And so you're going to have like epsilon h, epsilon h, epsilon h, or really epsilon h minus 1, epsilon h minus 2. Right? So intuition here is epsilon chance falling off the tightrope. If you fall off the tightrope, you incur a cost of h going forward. Right? And so the important thing to kind of note here is you're going to have epsilon h, you're going to have it h times, so you're going to have epsilon h squared. So this is for one time step, right? So this is saying at this time step, I had an epsilon chance of falling off. If I fell off, I encountered epsilon h cost. Okay? And I have this at all h time steps. I can fall off the tightrope at any point. Right? And so you're going to have epsilon h times h, which is going to give you epsilon h squared. Right? So all this is saying is that imitation learning, behavior cloning is bad. But we can make it better. Right? So behavior cloning as is going to give you quadratic error, which means that it's going to scale very poorly with horizon. And essentially the intuition is the same as the things shown here. It's just saying that if you make a mistake, you'll make a bigger mistake, a bigger mistake, a bigger mistake. It'll, you're way off the trajectory. So, one sec, sorry. Yeah, everyone follow that? Any questions? The proof here is not that important, right? Just kind of get the vibes. The vibes here are that you want imitation learning has this like compounding error problem and it scales quadratic. That's all you need to do. Yeah.
Can I clarify why we're using the horizon as the cost?
Oh, because yeah, it's a 1 if you don't do what the expert did, and it's a 0 otherwise. And so it's like a 1 for every step. And so you're going to incur 1 for every step in the horizon. Yeah. It's a great question. Okay. Everyone get that? Right? So, yeah. So the tricky bit with RL for language models is you're kind of treating it like a bandits problem. So you're like evaluating rewards on the whole generated sequence because sometimes partial sequences don't make sense. And so I think the compounding error problem in like standard RLHF is like less of an issue because you're not compounding or because you're like doing RL, treating the whole thing as like one step. So it's like one step RL, which means the h squared doesn't do that. Right. So that's I think in RLHF, it's more like it's more because your reward model is expected to generalize better than your dynamics model. So it's more like model-based RL than it is compounding error. But there's like newer things which try to like do partial credit assignment. And I think those things are more about compounding error. Great question. Cool. All right. So, oh no, I have a big circle. Okay. Okay. So essentially we can think of like the error of imitation learning in terms of these two factors. You can think of it in terms of an epsilon, which is telling you how likely am I to make a mistake, right? And you can think of it as an h squared, as in terms of like quadratic error over horizon, right? And so like the two things we're going to try and fix is we're going to try and reduce epsilon, and we're going to try and make this h squared better, right? So we're going to try and go from h squared to h. Okay. So the important thing here is that imitation learning is quadratically bad, and if epsilon is large, if you're not able to fit the data, you're going to be pretty bad too, right? So you want to reduce epsilon, you want to reduce h squared. Yes? Wait. Okay, so we're going to start with the first problem, which I'll call underfitting, which is basically the problem of reducing epsilon, right? And so the problem of reducing epsilon is saying, I have some expert, and I want to follow the expert as well as possible. But I'm not able to fit. I'm underfitting, right? And so how do I deal with underfitting? And why is that like not as trivial as just making your network bigger? So The next thing we're going to cover is multimodality and underfitting and imitation learning. And then we probably won't have time today, but we'll cover compounding error next. Okay. So the underfitting problem is trying to say if I have sufficiently complex data, just making your network bigger isn't going to fit it perfectly, right? And so why is that, right? So behavior cloning can underfit the data. So if epsilon is too big, we're going to have pretty large compounding error. So you might not be able to, get epsilon to be low. And I stole this from scaling laws in neural models, but neural language models. But in a neural language model, the bigger you make the model, often the better it is. Not always, but often. And it's really about like your capacity of your function approximator. But in behavior cloning, you'll find that often making the network bigger often doesn't make the problem better. And it doesn't just magically solve underfitting, right? So it's going to help in certain cases and not in others. But behavior cloning has a slightly strange phenomenon, or at least behavior cloning with standard mean squared error type things has an issue where it doesn't just get better the bigger you make the model. Yeah. So the issue is the following. Is that how expressive your policy is a combination of two things. It's a combination of your function approximator and your family of your distributions, right? So we said that we're going to have like linear models, tabular, neural nets, decision trees, whatever, right? They're going to be different function approximators. And they're going to be paired with the probability distribution. So we have like categoricals, we have Gaussians, we have diffusion policies, right? So they're all different, or diffusion models, they're all like different choices of our probability distribution. And what I'm going to posit is that just making your like neural net bigger, let's say you chose a Gaussian parameterization, just making your neural net bigger is not going to make your policy better, right? And so that's what's going to lead to the underfitting. Like a lot of times in behavior cloning, you'll use a Gaussian policy. And if you just make your neural net bigger, it will not make your performance better. So why is that? Why is that? Any guesses? So I have a Gaussian policy. There's a policy which is a neural net. Neural net maps to the mean and covariance of a Gaussian. And I have data from a human. And I just make the neural net really, really, really big.
Gaussian can capture the diversity.
Yes, that's right. Exactly. So Gaussian policy is often going to struggle in these kinds of settings. So like imagine that you are at an obstacle and you're trying to go left, or like there's two ways to solve the task, right? It's left or right. And your humans, some of your humans demonstrated left and other humans demonstrated right. And you like try to do behavior cloning maximum likelihood with the Gaussian policy. What's going to happen is that you're just going to average left and right, and you're going to go straight through the middle, right? And so what they often see in like these kinds of settings is if you have like choice points or bifurcation points, and you try to do Gaussian policy behavior cloning, which is the most common one, you'll see that it like does mode averaging. So if you have two different modes, you like average the mode, right? And so yeah, so the tricky part is that if you have these two modes, right, left and right, if you treat a Gaussian can't fit both of them. And so Gaussian's gonna average the mode. And when you average the mode, you're just gonna go straight to the middle. And so that leads to lots of problems where even if you make your model bigger, it's not going to get better because your distribution class wasn't rich enough, right? And so the first issue with behavior cloning is that you need to think about complexity of your policy, not just with how expressive your function approximator is, but how expressive your distribution is, right? Okay, so I'm going to argue that there's two ways to deal with this, right? Does this problem make sense to everyone? You have left, right, Gaussian, average, goes to the middle. Okay, so I'm going to argue that there's two ways to deal with this. The first is through distributional expressivity, which means that I'm going to use something better than a Gaussian, right? And the second is by changing the objective. So the objective right now is this maximum likelihood objective, which is going to take us right in the middle. It's going to do mode averaging. But if we change the objective, I'll show that we can kind of like do mode selection. So either pick left or right, right? So if you choose a objective carefully, you can go either left or right. And then if you choose a more expressive distribution class than a Gaussian, then you can represent both left and right. So there's like two ways of solving this problem, but essentially it's because your distribution class is not expressive. Okay. I think this is a good point to stop because we won't get through everything in the next 5 minutes. But yeah, any questions before we end? Cool. All right. Thanks, folks. And we'll keep having class here from now on. So yeah, please come here.
Sit down and ask your TA about doing some more questions.
Yeah. Of course. Yeah. I think I have office hours tomorrow and Friday.
Okay, I don't know if they're posted on the website.
They're not on the website yet, but they're on my first lecture slides. I think Jacob is out of town today, but he'll be back. So he'll pop there, but just look at my first lecture slides. I think it's Tuesday. Let me